All right, so today we're going to be talking about percent yield. Couple vocab terms to know before we get started with this is first one, theoretical yield. That's the maximum amount of product that could be formed from given amounts of our reactants. Okay, and this is calculated using either the limiting reagent process that we talked about the other day, or just regular old stoichiometry. Okay, so this is what we've been doing in class for about the last week. Okay, we've been finding theoretical yields. Okay, the actual yield, that's the amount of product that actually forms when the reaction is completed or carried out. Okay, so for our purposes today, all of the actual yields will be given in the problem. Okay, however, when we're in the lab, the actual yield is what you get from the reaction. Okay, the mass that we record from the problem. Okay, and that's what we'd get using our balance to record, whatever we get from the reaction. Okay, and the theoretical yield is what you calculated beforehand. Okay, so what we want to know then is how much of the product did we actually get compared to what we should have gotten, and that's what we call the percent yield. All right, it's just the ratio of actual yield to theoretical yield multiplied by 100%. All right, now remember that the percent is just a unit, so don't hit the percent button on your calculator. Things will get all wonky-jawed.
Times 100.
Yep. So when we times it, just times it by 100. Don't hit the percent button. Okay. Pretty basic, pretty straightforward. So let's look at our first example problem.
Yeah. Again, you've been doing this the whole time. The only thing we're doing is we're just adding this formula right here.
Word. All right. So example 1. If 50 grams of silicon dioxide is heated with an excess of carbon, 27.9 grams of silicon carbide is produced. What is the percent yield of this reaction? Okay, so there's a couple key terms in there that I want you to be aware of. Number 1 says with an excess of carbon. Okay, so we've already determined in this case what our limiting reagent is. If we have excess of carbon, that means that the silicon dioxide must be
the limiting reactant.
The limiting reactant. Okay, so we're going to use that limiting reactant to determine our theoretical yield, what we should actually get. All right, so this is going to be your straightforward stoichiometry problem.
Now, one thing you might just be might be a little bit confused on, what are you solving for? It says what is the percent yield of this reaction, and if you don't know what you're solving for, it's always for the information where the product is given. Since we are given information about this product right here, that's what that's what you're solving for.
That's what your theoretical yield should be.
Is.
Okay, so we want to know first the theoretical yield of silicon carbide. All right, since we already know the actual yield. So we'll do our stoichiometry conversions here. And I'm not going to talk very much here because you should know how to do this. All right, so we're going to divide by the molar mass of silicon dioxide, which is 60.1. All right, then we'll multiply by our mole ratio.
Mole ratio.
All right, and that's going to be
1 to 1.
1 to 1,
nice.
Absolutely. Pretty easy there. Okay, and then we want to find the mass of our product, silicon carbide. So we're going to multiply by the molar mass of silicon carbide, which is 40.1 grams. Okay, and we arrive at an answer of 33.4 grams of silicon carbide. All right, and this is our theoretical yield right here. Okay,
this is what we're supposed to get.
That's what we should get. Now, if we read the problem again, it says that we actually got 27.9 grams that was produced. All right, so we need to plug this into our percent yield formula. So we do actual over theoretical. So 27.9 grams.
Remember the formula?
They already had it.
Okay. So we have 27.9 grams.
That's our actual yield over our theoretical yield, 33.4 grams, times 100.
100.
All right, and then remember that percent sign is a unit. All right, so when you do the math here, you should come out to 83.5%. All right, so what that's telling us is that in our reaction that we did in the lab in this case, we got 83.5% of the product out of that reaction.
Or you recovered it even.
Or recover. That's a really good word. Okay? So,
I know.
a couple of different reasons that we can talk about real quick, because this will be needed to be included in lab reports. We could have lost some of the product because we didn't react it completely, or it wasn't finished reacting. Maybe we pulled the Bunsen burner away a little too early.
Filtering.
Filtering is also another way. Sometimes you don't get all the filtrate out. What else? Impurities.
Someone knocked it over.
Somebody knocked it over. Human error. A lot of stuff could have happened there. So, all right, let's look at a second example. All right, so in this case, we've got a lot of numbers in here. So let's decipher it all together. You have 30 grams of aluminum and 64.5 grams of chlorine gas. All right, the actual yield is 42.9 grams of aluminum chloride. What is the percent yield? Okay, so the first thing we're going to do here is we're going to write down all the masses underneath those particular substances. I know. It's doing a lot. Okay, so notice here that we have two givens with our reactants, 1 and 2. All right, remember we talked about the other day in limiting reactant problems that this is what you need to recognize so you know when to do a limiting reactant process. All right, so we've got our actual yield up there. We've got our two reactants. So step 1 is going to be to determine the limiting reactant. Okay, so that's the first thing we're going to do.
Okay, so
Do it up.
Oh, I'm sorry. Go ahead.
No, I was just saying do it up.
Okay. So remember, what we have to do is convert substance 1
To moles.
to moles. So we have 30.0 grams of aluminum, and I'm going to
Put the molar mass in there. 1 mole.
mole of
27.0 grams.
Al.
Yeah.
Cancel. And when you divide those two numbers, you get 1.11
Moles
moles
of
of aluminum.
aluminium.
Okay, now we
If you're from Britain.
take aluminium.
I'm sick. I'm sick.
Okay. 64.5 grams of chlorine gas. And we're going to put 1 mole of Cl2. 71.0 grams of Cl2 on the bottom. That cancels out. And I should have here about 0.908 moles of
CO2.
Cl2.
All right, so now what we have to do is we need to do our comparison here. So we'll need to convert the moles of aluminum, moles of answer step 1. We'll need to convert that into moles of chlorine.
Yeah, to see how many or how much aluminum is needed to react fully with 1.11 moles of aluminum.
Yep.
So let's change colors.
Change the color.
So let's put 1.11 moles of aluminum. Use the mole ratio. It's big X. And let's see, it's a 2 to 3, so 3 moles of
chlorine.
CO2 on top, 2 moles of aluminum on the bottom. That cancels out. Multiply, take 1.11 times 3 divided by 2, and I should have
1.67.
1.67 moles of Cl2.
All right, so then remember the next step in determining the limiting reagent is to look at what you have and what you need. So in this case, we need 1.67. We have 0.908. Do we have enough?
Ain't got enough.
Ain't got enough. All right, which means Cl2 is our limiting reactant.
Okay.
Okay, so what we're going to do now is the limiting reactant is going to be what we use to determine our theoretical yield. Okay, so you can just erase that.
Let's go to the next page.
Okay, so we're going to use chlorine.
You rewrite the equation. Plus 3Cl2, your arrow of 2AlCl3.
Okay, and remember we have how much AlCl3 there? 42.9.
You have 42.9 grams of this stuff,
And
and
we have what? 0.908
0.908
moles.
moles.
Yep. Okay, so we're going to use our limiting reactant here to find our theoretical yield.
So we put
0.908 moles. Okay, you'll notice that we started with moles. If you wanted to start with the grams of Cl2 because this is a little too confusing, that's all right as well. Okay, we just took out the first step since we already converted it to moles.
And I write too big anyways.
And Herzog writes too big anyway.
So 2.
All right, so we'll do the mole ratio here.
Oh yeah, let's take a look. So I have a 3 to 2 mole ratio, so it's going to be 2 moles of AlCl3 on top and 3 moles of Cl2 on the bottom. That cancels out. We're left with moles of AlCl3, and I have to convert that to grams.
Yep, because our yields are always masses. Okay, so another key point there.
And what is the molar mass of this? It's 133.5 grams. AlCl3, moles cancel out. I'm going to take 0.908 times 2 divided by 3 times 133.5, and I get about 80.8
grams of aluminum chloride. All right, so there's our theoretical yield using our limiting reactant. So now we need to take our actual yield, in this case, 42.9.
42.9
over
grams.
Yep, over our theoretical yield, 80.8
grams
times 100.
Times 100.
And that comes
That's not
out
a very
to,
good number.
that's all right,
53.1.
3.1%.
That means someone sucked at this lab.
Yep, that's not good.
No.
Okay, so these are the only two type of problems that you'll do. So either it's straight up stoichiometry, or you got to find the limiting reagent.
And then you do the stoichiometry.
And then you do the stoichiometry, and once you're finished with the stoichiometry, you use that theoretical yield that you just calculated to find your percent yield. Cool beans? All right, we done.